Thank you. Yeah. So thanks for a very nice, very kind introduction. And thanks for inviting me here. So in my lecture today, I'm going to focus on this so-called self-evolution of large language models. Meaning, where we can have this LM to self-evaluate its own response, to do self-refinement, and improve their reasoning capabilities over the time with minimum human intervention. So for LLM self-evolution, you can imagine there are two different setups. In the first setup, where we will still have this training phase, so in order to train LLM, essentially that means we would need to have some way to automatically generate training data for LLMs. So here, basically like we show a kind of a loop here, right? So essentially the first step is to create some synthetic data by self-output. So for example, LM performs self-play. They can generate this kind of synthetic data. But then one natural question you want to ask yourself is how to construct effective this synthetic data set by for LM training. And then the second step is after this kind of synthetic data are collected, so you probably likely will need to have some way to refine the data, right? Because not all the data comes with a very high quality. So that there will be some way to filter out this low quality synthetic data. And afterwards, we can use this generated synthetic data to train the model. And at the end, then we will need to have some way to measure the progress of the model, and then to have this appropriate kind of performance evaluation approach to measure the model progress. So that's just the first kind of a scenario where we will need to train LLM. The second scenario here is there's no training. So you can imagine this is just kind of a pure software LLM inference, right? So here, when we talk about LLM self-evolution, you can imagine this kind of a loop, right? So user first feed a query to LLM. LLM generates some initial response, and this response will then be evaluated by LLM again. So it could be the same LLM, could be another LLM as a judge. The evaluation result will be fed to LLM again to generate this reflection data. And then this reflection data can be used to modify the LLM's output, right, to do the refinement. Sometimes people also refer this as the verbal reinforcement learning, right? So basically this kind of a supervision signal or reward signal pretty much expressed as kind of a textual feedback. Okay, so in my talk today, I'm going to focus on four topics. So the first one, I will start with this synthetic data generation. So how we will be able to create some synthetic data to train LLM, to fine-tune LLMs. And then the second one will be this inference time self-reflection and refinement. So here we don't need to train the model. But we need to have some way to collect this verbal feedback in order to improve LLM's reasoning capability in the next iteration. And I will also cover a continued learning approach to self-update the model. And finally, I will discuss this meta-reasoning in LLM. Okay, so let me start with the first one, synthetic data generation by self-play. So one kind of a classic paper, although the paper was actually published 3 years ago, but then can already consider as classic. So there is this star approach, or the technique so-called the self-taught reasoner, which relies on very simple loop. Right, so here we can see that basically what they did is you can start with some question, feed into LLM, and then this LLM will generate some rationale as well as answer. But in this case, they have some ground truth answer, right? So essentially, they can compare this answer generated. If it matches the ground truth answer, then they would just consider this generated rationale and answer to be correct, so as kind of a pseudo label. Then they can add it back to their training pool, and then in the next iteration, they can further fine-tune the model. However, if the answer is wrong, so what they did is that they would just fit in the correct answer, ground truth answer, as a hint to the language model, and then ask the language model based on this input and expected answer, then what would be the rationale? So, and then in this case, again, they just add this LLM generated rationale and answer back to the model to do the fine tuning, right? So this is a very kind of a simple approach to generate some synthetic data to train LLM. And later, then there's an approach like a so-called self-instruct. We know that at some point, right, so there's a lot of approach being proposed for instruction tuning. Basically, we want to have the purpose is to enable the LLM to follow the instruction. So for this self-instruct, what they did is that they started with this so-called seed kind of instruction, right? So they have some seed set of tasks, and each with one instruction and some input-output example. And then these are just sampled to prompt the LLMs to generate the new instructions and new examples. They have two different kind of approach for output first or input first. So this is really just for different tasks. And for the output first, usually I think this task is for kind of a classification task. And what they did is that, for output first, they give the instruction and provide the kind of a class label and the input, and then ask the model to generate the output, right? So the output here referred to the class label. So class label is actually provided to the LLM for synthetic data generation. And if it's input first, then here is usually like the task is relating to kind of a text generation task. And in this case, they just did not provide any particular class label, and then they just prompt the LLM to generate this input and also output pairs. And afterwards, then basically they would need to have some way to do the filtering, right? So the ensure the quality of the synthetic data is good enough to fine-tune the model in the next generation. Of course, once they have done this kind of data collection, and basically, there is an issue. If you just use the same LLM to keep on generating its own training data, then they will observe this so-called performance plateaus, right? Because of this reduced data diversity. As you can see from the kind of a figure here, so they've done the experiments on using 3 different language models, Phi-3, Mixtra, and also Llama-3. So you can see these kind of dashed lines. So those are the result generated by training the LLM on its own generated synthetic data. So the mitigation strategy they used is this so-called multi-agent fine-tuning. Instead of just using the single agent to generate synthetic data and then to kind of continue to train the model in order to self-improve itself, what they did is they have multiple agents, and then each agent actually kind of generate diverse set of data. So you can see from the architecture here, right? So they have 3 different stages. In the first stage, give the same question, they actually fit into 3 different LM agents here. And then those agents, they will generate some kind of output, and then they will start to have some kind of debate among themselves, right? And for the generator fine-tuning, you can imagine that for different agents, because they kind of generate different set of synthetic data, right? So there will be some kind of a diversity. And also because you can use the LM agent as an evaluator again, right, to critique or to judge its output. So then they would have another kind of a loop to do this critique fine-tuning. So in any case, they observe that if they involve multiple agents for this synthetic data generation and also for this kind of LM output evaluation, they can observe better results. Right. So then we know that, like, in the kind of like a previous example, right? It's more like we have this LLM to do the self-evaluation, generate some kind of a feedback. And we can use this feedback as kind of an implicit preference as a supervision signal to train the reasoner. So the reasoner here is just a kind of, you can imagine this is kind of like generated, right? So we use the reasoner to answer the question given by the user to generate some kind of response in relation to the user's input. However, we can also see that we could have this verbal reinforcement learning, right? So in this case, instead of just having this, the single reasoner to generate the response, we would have a critique here to evaluate the response generated by language models. And these verbal reflections can be fed into the reasoner to improve its response in the next iteration. Right, so this is a so-called explicit verbal reinforcement learning. So one kind of a simple approach you may imagine here is we could have two different models, right? So one model is called the reasoner. It's just to perform the task and then to also reflect on the errors and in order to do the refinement. And we could have a separate critique which perform the evaluation, but also decide on when to stop the iteration, right? Because you can't just do this iteration endlessly. So you need to know which point the answer is good enough, then you like exit from this loop. However, so before I talk about this, I will first introduce the particular kind of a task we focus on. So the task we want to do is a scoring of science exams. The problem setup looks like this, given some question, right? And usually there will be some key answer elements provided as well, and also the marking rubric, essentially just to compare the student answer with the key answer elements to find out how many key answer elements can be found in the student answer. Then the corresponding kind of points will be assigned to the student answer. So you can see that this really involves two steps, right? The first step just compare the student answer with the key answer elements. And then the second step is to apply the marking rubric and generate the scoring decision with the rationales. And we prompt ChatGPT to do this. And this is the kind of a result given by ChatGPT is actually quite impressive, right? So ChatGPT will perform this kind of element-wise comparison, right? So you just like compare the student answer with each of these key answer elements to see whether that has been mentioned or not mentioned, not appear in the student answer. And the second step is to apply the marking rubric to generate the answer rational decision. So it's already quite well. But then we know that language model hallucinate, right? As I'd already presented in his first talk. So there's a hallucination problem, and basically, we can't just take the ChatGPT's result directly. So the next thing we actually do is maybe we can use stronger LM as critique, right? So here we just use GPT-4 as critique. However, when we use the GPT-4 as a critique, we see that if we ask the GPT-4 give us kind of an evaluation on the this assessment model outputs, right, and then use this as feedback and then ask the model to reflect its previous kind of a response and then to do the refinement. There's no guarantee that it will observe increased performance. So over the iterations, we actually see that the performance even degraded, right? So basically, if you just take off the shelf LLM as critique, there's no guarantee you will have this improved performance. So the issue here is, I think the issue here is that the GPT-4 generate a kind of a feedback often appears to be quite superficial, right? So it did not tell you, the reasoner where the error might be and then what kind of correction it should do in the next iteration. So then the question for us is whether we will be able to generate some kind of a high quality reflection data, which can be used to train the model, right? Train the critic, and also train the reasoner as well. So what we did here is we, instead of just feed the student answer to the kind of marking like assessment model to generate the mark and rationale in one go, well, we can decompose this problem into multiple binary decision problem, right? So given the student answer, what we did is we could like reframe it as a multiple kind of a binary yes or no question, right? So we just like feed into each key answer element and then ask, whether the student answer contain this key answer element, yes or no, right? So this is much more simpler. And we could also prompt LLM to do this multiple times. And you can imagine that if you do this, then you will actually end up with this kind of we call it thought tree, right? So it's kind of a tree structure. And because you do multiple kind of sampling, right? So in each kind of a sampling stage, you may get yes or you may get no, right? For when you ask the language model to compare the student answer with the same key answer element, right? And once you have this kind of tree, kind of thought tree, you can, sort of like follow the one particular tree path and apply the marking rubric. You get the final score. And some of the scores will be correct and some of the score could be wrong, right? So now you actually know which path give you the wrong score, which path give you the correct score. And you can actually ask language model to just do the comparison to see, where it did this judgment wrong. And then this kind of difference can be summarized as the guidance for correction, right? So essentially, in this way, we will be able to generate, we call it a more actionable kind of feedback, right? So the feedback would be able to localize where the error could be, and then could also suggest what needs to be done in order to correct the error, right? So once we have generated this kind of a synthetic data, you can imagine. We only show just one round of this kind of evaluation and also refinement loop, right? So started from student answer, we have the reasoner generate the initial kind of marking decision and rationale, and this is wrong. So we have a critique actually to generate the feedback and then suggest localize the error and also suggest the guidance for error correction. And then the reasoner would take the guidance from the critic, right, to refine the answer. And finally, critic would decide whether it should stop, this iteration. So once we have this kind of synthetic data, you can imagine that we would then use the sort of this kind of student answer, and then the initial output from reasoner as the training data, right? So this is kind of input-output pair to train the reasoner. But we could also use the student answer, reasoner's initial response, and critique the reflection and reasoner's refinement as training data to train reasoner again, right? So this is just a teach reasoner. If there's some kind of feedback available, then how it should modify its response appropriately, right? And similarly for critique, we could also do, using this kind of student answer initial response from reasoner, and then the critique the evaluation results as the expected output, right, to train the model. But we could also use all these 1, 2, 3, 4 as input, and then 5 as output. So this is teach to critique when to stop this iteration, right? So once we've done that, we can actually compare our approach with the previous baseline where we simply just use GPT-4 as a critique, right? As we showed previously, GPT-4 usually requires 3 to 4 iterations in order to stop further kind of answer refinement. And still, it can't guarantee to have increased performance. However, using our approach, then majority of the time, we only just need a single iteration, and we can reach a much better performance compared to the baseline approach. Right. So this is just to show you how to generate some effective synthetic data in order to allow the LM to improve itself. So the next topic is on this inference time, self-reflection, and refinement. So let me just start with a very basic LLM prompting. We know that simple prompting, meaning you just give a question right to LLM and ask LLM to give you the answer. Or you can do this train of thought prompting, right? Just adding the phrase like let's think step by step, then LLM would likely to have a better results than the previous one. But how about this LLM self evolution, right? So as I just described it to you earlier, we can get the LLM to generate results and then do this self-reflection and do refinement again. And you can do this, multiple iterations. So in this self-reflection kind of loop, we know there are few key factors, right, in this iterative process. The first one is evaluation, really, to give you, good quality kind of evaluation results. And then this reflection generation. So the reflection should somehow give you more kind of actionable, guidance for the generator to improve its performance, right? As what we have seen in our previous work. And then the final is this response refinement. So it should need to, take into account the reflection and then to refine its own output. But so here, obviously, we only focus on inference time. This is no training, right? And self-evaluation actually has limitations, as we have noticed in our previous work. So here, the dashed line here is actually shows if you give the LLM ground truth, meaning if LLM generates some results and you have ground truth, you know whether this is correct or wrong, right? And then you give this accurate signal to the LLM, then yes, LLM would be able to improve its performance over the time. However, if you don't have a ground truth, which is basically what we usually will face in the real world kind of evaluation of scenario, then there's then basically LLM would not be able to, most of the time, would not be able to improve its performance through this kind of self-evaluation, self-refinement loop. So we just try two simple prompts. So the auto prompt here, meaning we ask the LLM to kind of evaluate its own answer. Right? So it could be correct, it could be wrong. If it's wrong, then you will need to refine its previous answer. And then the never stop, meaning we just tell LLM you failed in your previous attempt, then you need to consider a new answer. I think the rationale here is that if LLM's previous answer is correct and LLM has a very high confidence, then even though we tell it your previous answer is wrong, LLM should still stick to its original answer. That's what we expect LLM will be able to do, right? But then what we notice here is basically if we don't have a ground truth validating these LLM outputs, then LLMs actually struggle to consistently improve its performance. So the other kind of things we observe here is even though even when the ground truth label are available, and then we tell LLM is previous answer is wrong, you need to refine its answer. LLM often still fail to just follow our instruction. So this is just another kind of finding we have. So what we propose here is this so-called multi-perspective self-reflection approach. We call it mirror. So in this kind of self-evaluation, self-refinement loop, what we now need to do is we have some navigator try to generate this diverse question-specific direction. So we kind of prompt the LLM to think about solving this problem from different perspectives, from different angles. And then this reasoner would just generate response to the question, and then by following this particular kind of direction. The evaluator here, we have defined three different types of rewards, right? So there is a so-called interconsistency, meaning because given the same question, we ask the LLM to solve the problem from different perspectives, right? So then there is a agreement among responses from multiple perspectives, and we have this intra-consistency because we could do this in multiple loops, right? So then we will need to check the LLM self consistency following the one particular path, right? So you can imagine we actually will be able to check the consistency along the different kinds of tree branches. So that's by horizontally, right? And then we can also check the consistency vertically, follow some specific paths. And finally, we have this reward relating to diversity because we need to ensure these question-specific directions, they are different from each other. Right? So we need to encourage this kind of diversity. And the stopping criteria is just based on the consistency among the states. So we can see how this performance works. The top one, I'll just show you the self-correction, right? So this is just a baseline. We ask the LM to do the self-evaluation and then to do the self-improvement. And here we just show, one iteration, and then it just it wouldn't be able to correct the previous wrong answer. And then the bottom one is our proposed approach. So essentially, give the same question. We branch out to multiple responses that follow different kind of perspective or follow different kind of directions for solving the problem. And then we have a multiple iterations. Then basically you will see the tree will keep on growing, right? And then we can track the consistency of the answers across all the branches. We could also check the consistencies along each different kind of tree paths. Right? So that would actually give us better results. So the next one is actually this so-called continual learning with self-updating models. I'll start with this test time reinforcement learning. I think this work was kind of published on arXiv this year. So what they did is this is simply during the inference time, and then they explore that LM can actually self-evolve just by using its priors from the pre-trained data. So and they actually have a quite impressive results on, but all this on the math data sets, right? So you can see those are the baseline results. This light blue color and then darker blue color shows using this their test time reinforcement learning, they observe quite significant performance improvement. What they did is actually approach itself is very simple, right? So give the LLM parameter is frozen, and then they can prompt this LLM multiple times, right? And then they generate multiple answers. And for these multiple answers, they can just take majority voting, and then this kind of the answer, the final answer derived by majority voting will be used as kind of a signal for correctness, right? They assume this this answer derived by majority voting is correct, then that actually would give the kind of a reward, right, to ask the LM to actually do the parameter update based on reinforcement learning. So they have a more kind of details of explaining how these things work, right? So essentially LM just predict multiple answers, but then they use the majority voting to derive the final answer, and then they can then calculate the reward based on this this derived kind of a pseudo answer, right? So this reward signal would then be used to train the LM to update LM parameters through reinforcement learning, right? So, and they observe quite very encouraging results. Okay, right. So we actually know that that kind of approach somewhat replicate or mimic what DeepSeek R1 was doing, right? So DeepSeek R1 actually they introduced this so-called post-training paradigm. They call it incentive training, right? So this incentive training, essentially they compute the rewards just based on the final answer part of the language models, right? So essentially how this did is we start with this kind of give the user's prompt right to LLM, and LLM generate the reasoning parts. like the intermediate thought processes and also the final answer token as well, right? And then they have some verifier, right? So usually I think DeepSeek R1, when it was just published, primarily focused on the mathematics and coding tasks, right? So you can easily like get some kind of ground truth or external verifier to verify, whether the answer produced is correct or wrong. And this gives the reward signal, right? And then these rewards can be used to train the LLM through reinforcement learning. So that's how this incentive training works. Right? So for the incentive training, in fact, like most of this incentive training, they rely on this some kind of we call it verified reward. So they require some external verifier to give you the accurate reward, right? So here I just show some, I think the data sets and then also the models. In fact, like a majority, almost like all of them, the majority of them actually focus on the math and coding tasks, right? And then in terms of reward they use, I think all of them use accuracy, and some of them also use the format, right? But then in any case, they would like require some kind of external verifier, give you very accurate reward. But the problem is how to extend this incentive training beyond the math and coding, right? So in this case, the answers are actually free form, and it's very hard to verify. So think about those, like, I just listed some example tasks here, which, like, this is so-called the free-form reasoning tasks, right? So I think, it's, for example, like the first one, the question here is to ask the LM to discuss something, right? And then you can imagine like the answer would be some kind of a free-form text. And then the second kind of like task is to ask the LM the why question, right? Ask the LM to elaborate on the cause or the reason behind. And then the third task is kind of like creative writing, right? To ask LM to create some engaging story. And then last one for machine translation, right? So for all these tasks, we see that they are different from mathematics or coding tasks where you have a very accurate kind of rewards, right, to decide on what kind of error signals you want to propagate to the LLM for training. So how to do it? And we actually propose this so-called NOVA, right? So no verifier reinforcement learning, and the work was led by my PhD student Wei Liu. So essentially, like the idea is actually very simple. What we want to do is just use the reasoning perplexity as the reward signal, right? So essentially, give some prompt to the LM. LM will generate the reasoning tokens, right? Intermediate thought process, and generate like the final answer. So here, instead of like using the LM generate a final answer, we replace it with the ground truth, because for most of the tasks, we also have some kind of a ground truth as well, right? And then we can actually compute this so-called reasoning perplexity, right? So assuming this ground truth is actually generate the following is a reasoning parse, then what would be the perplexity value? And this kind of like setup would allow us actually to do the general reasoning across any fine-tune, supervised fine-tuning data, right, using this same approach. So essentially, like we basically need to use the reasoning perplexity, construct two different types of rewards. So here we can see we have a policy model. So policy model is kind of like to generate this like a reasoning parse. And then we have the proxy model. So that's just for the kind of reward calculation, right? These two models, they are same. But then because like during the training, we need to update the model parameter, right? So usually like we need to kind of decide on how frequently we want to update the like proxy and also policy model. So although they are the same, but then we actually like to update the model parameter in different kind of intervals. So you can imagine that like we update the policy model more frequently, and then every like a few iterations, then we would like duplicate this model parameter to this process model, something like this. So for the rewards, we have this reasoning reward. Basically, like this is just purely based on the perplexity value. We also have this kind of efficiency reward, right? So this is just like try to make the reasoning more efficient rather than some models may generate like over long kind of a reasoning process, and we want to penalize this kind of results. Similar to DeepSeek R1, we also have this format reward as well. So we can see what these results look like. So what we did here is we actually want to see, using our approach, whether these the reasoning kind of patterns will be more diverse. So generated from this LLM. So what we did is, using the model, it would generate like lots of kind of reasoning traces, right? We actually used the JAMA model, JAMA 2.0 Flash, to summarize these reasoning patterns. So kind of like we asked the JAMA model to analyze this reasoning pattern to see if it can like cluster this reasoning pattern into different groups, different categories, right? So here we actually used a different color to denote a different reasoning pattern. And what we can observe is initially, right? So in the earlier training iteration, then the training kind of reasoning patterns is dominated by this what we call decomposition pattern, right? So the model tend to generate something like let's break down the process step 1, step 2, step 3. However, like while the training progress, we start to see some other reasoning patterns emerge. Like this pattern, we call it direct, right? So basically like generate some kind of a direct answer. And then we also observe, I think, another reasoning pattern. So this is kind of enumeration, right? So like one common use and then another common use and so on and so forth. And then we also like see there is another like reasoning pattern called reflection. Right? So like for example, language model may generate something like, however, it's important to know something, may use it like differently. And also this red one, which is the assumption kind of a reasoning pattern. And then I think the final one would be this causation. So in any case, what you would observe is through this training, like a de novo tend to produce more diverse kind of training patterns compared to the original model. Of course, like we have more results in our paper. If you're interested, you can check. And I think finally, I actually want to like talk a bit about meta reasoning in LLM. So let me start with some LLM reasoning open problems. There are lots of problems, right? So, but then I just like focus on a very few of them. So the first kind of the problem is LLM actually like exhibit some kind of a phenomenon, but then they actually like lack this cognitive kind of attributes such as awareness of limitation. So meaning LLM tend to be either overconfident or underconfident about their responses. Right? So this kind of figure actually illustrates the LLM's confidence, estimated confidence versus their accuracy. So ideally, we want the LLM's response to align with this triangular line, right? So if the accuracy is low, then LLM should be less confident about its response. If accuracy is high, then LLM should be more confident. But then we can see for the JAMA model, then it's just like tend to be overconfident all the time. And for a Llama model, I think what you would observe is for lower accuracy, it's actually like it becomes kind of overconfident, right? And higher accuracy becomes like underconfident. And Claude like might be better, but then still, they don't kind of like strictly sort of like align with this triangular kind of ideal sort of situation, right? So another open problem here is I think lots of people also observe that although sometimes you think this is so-called train of thoughts, or you ask the model to do more elaborate kind of thinking, it will give you better results. But then this is not true all the time, right? So I think in this paper, it's very interesting. They actually found that even for humans, sometimes for certain tasks, if you ask the human to think twice, it will actually give you the wrong answer, right? So they probably some of the answer actually just require very kind of instinct, sort of a direct response generation. So I think they focus on one task here is given some kind of human's portrait, and then they just ask the human to identify from a set of candidate images which one matched the given image, right? So what they observe is the LLM actually exhibits the same kind of issue, suffer from the same issue as humans, right? So I think they've done the experiments on GPT-4o, Claude, and Gemini, right? So if you ask the LLM to do the zero shot, they actually give quite good results, especially for Claude, right? But then if you ask them to do COT, then you will actually see the performance drop. So again, you can see, right? So the LLM actually need to do this so-called adaptive reasoning, right? So they need to decide on when they should generate the answer straight away, when they should do more kind of elaborate thinking. And another example is we see to improve LLM reasoning, lots of approach actually make use this reinforcement learning. Right? Reinforcement learning will require rewards. But then I think this issue about reward hacking, right? So essentially, the agents, the LM agents, actually kind of exploit the flaws in the reward function without actually, in order to achieve higher score, without actually learning the transferable sort of reasoning patterns. Some people come up with the approach such as using the ensemble of reward models, right? So you can imagine that if you want to train some reward model, the simplest way is that you can start from different random initialization of the parameters, right? And then you train the reward model, and you will end up with a set of reward models. And what they did is, they can get this, a set of reward models to give the reward value, and then at the end they just do the ensemble, right? Aggregate all these reward values. But sometimes it works, the first kind of instance, right? So the LM response supposed to get a lower reward, and so that works. But sometimes they didn't, right? Like in another example, so even the reward ensemble, they all give a kind of positive rewards. While in reality, you would expect the reward for this particular response should be low. So it actually fails, right? So I guess this is still the open problem. And then another kind of open problem is this LM's difficulty in internalize new knowledge, right? So in this paper, actually, they show that for two different tasks, right? One is on safety alignment. The other one is, for instruction kind of a tuning, right? So what they found is if you train the LM for safety alignment, right, and you actually achieve 100% accuracy, but then if you continue to train the LM with this, I think AOA alignment is just an absolutely obedient agent alignment. So I think in this case, they just fine-tune the LM on 10 harmful examples, and the LM's performance on the previous safety alignment actually dropped to 0%. And then in the second case, if you train the LM first on finance QA, LM can achieve 75% accuracy. But then if you continue to train the LM on science QA dataset, you will see the LM performance, on the finance QA would drop to 0%, right? So it's basically if you continue kind of update the LM, and then in hoping it can acquire, to learn some new knowledge, then they would suffer from this kind of catastrophic forgetting problem. But of course, like in the paper, what they did is that they actually realized that they realized that I think for the LM like a model training, they would need to fix or freeze the bottom layers of the transformer architecture, and that would actually lead to substantial improvement in terms of like kind of recover the LM performance on the original tasks. Right? But then still you can see this kind of continue training the LM, but they still ensure it would like update its parameters to reflect the new knowledge while keep like memorizing the old knowledge is still a big issue. So what we are doing here is actually we want to draw some inspiration from cognitive science research, right? So I think in cognitive science research, there's lots of study to look into the human meta reasoning, right? So we know that like for the human reasoning, usually like they start with identifying some components and goals, and then generate some initial response. And then if necessary, they will perform some analytical processing right before making the answer choice. The metacognition actually like has two different levels, right? One is this so-called object level. The other one is this meta level. So the object level meaning, it's more like they do some kind of a perceiving, remembering, and deciding. But the meta level process, then they will need to monitor and control them. So that's why you see this meta level metacognition monitoring and also metacognition control, right? So the monitor usually like work in the background. They would like to signal some confidence or doubt. And then human would either like act or seek more information, adjust their previous reasoning strategy, or just give up, right? So and then for the like kind of controlling phases, then basically like those are the kind of control functions relating to different kind of monitoring processes. So we can see that all the monitoring process actually like reflect some subjective assessment, right, of the probability of success or failure when solving the task, right? So either before, during, or after engaging in the task. And this kind of assessment would then trigger a variety of kind of controlling decisions, right? So, such as taking some action or allocating sort of like more resources, or making different choices of this reasoning strategy, right? So, intuitively, you can start to think about maybe these kind of things can also be translated to train the LM with meta reasoning capability, right? So in this case, what we propose here is kind of like a cognitive architecture of LM meta reasoning, right? So it involves two different levels of tasks. One is the meta level, the other one is this task level, right? So before actually like generating some reasoning steps for a given kind of question, then we have the LM self-awareness, right? So it first needs to assess its own kind of knowledge, need to kind of review its own knowledge. So whether this is solvable or beyond its capability to solve the problem, and also initialize some reasoning strategies. And then given the strategy, then LM will take the actions, right? Now this kind of monitoring will come into place. So the monitor will track and evaluate stepwise kind of reasoning using some reward function, and beyond this sample-wise annotation. And the evaluation and regulation there would then kind of look into this sort of like reasoning kind of processes, and then perform error pattern detection, correction. And these observations can be fed to this meta reflection, because there might be some kind of error patterns which is common across multiple tasks, right? And then at the same time, could also like update its meta rewards. So this is actually kind of like we the position paper we just published in this year's ICML. Right. So what we propose here is kind of like we can actually frame it as a Bayesian learning framework, right? So in this case, LM actually need to have some memory. So this memory, we split it into two different views. One is this internal view, meaning like the LM's own kind of foundational pre-trained knowledge. And the other one is this external view. So this is kind of like task-specific knowledge, LM or some kind of dynamic knowledge, while the LM actually like learning through this problem-solving process, right? So for the Bayesian learning, then the first step we actually like need to update the reasoning strategy at the task level, right? So the F is actually kind of a tailored reasoning strategy for the input. This is actually conditional on the sort of like observations and also the LM's internal and also external views, right? So kind of knowledge. And then so given this reasoning strategy, then we also like need to so-called update the knowledge prior at some kind of a meta level. So usually this is the kind of like we need to consider so by multiple possible reasoning strategies, right? And then use those as a kind of signal to update the LM's knowledge priors. So now I'll just give a slightly more detail about each of these steps in this meta reasoning framework. So for the self-awareness, in fact, like there are two different kinds of we call it like a solvability, task solvability, right? One is a so-called capability aware solvability. So this is more relating to LM's uncertainty, confidence kind of scoring. But the other one is a so-called mission aware solvability. So even though like for some particular task, LM can solve the task, but the LM may still need to reject to do so, right? Usually like due to these safety issues or some kind of like a jailbreaking attacks. And then the second one is about this kind of how to initialize reasoning strategies. So here, like we just like list some, kind of possibles of like a reasoning strategies. There could be like a planning. There could be some kind of require a bit of like a knowledge retrieval or require integration of the tools, right? So essentially, like you can imagine, this is a LM may require, like a different set of skills, but then this kind of like a skill combination might be, that this could be done in some kind of latent space actually. And then the second step is the monitoring. So for the monitoring, usually like given this reasoning strategy, the LM start to perform some action, right? And then this monitoring will actually assess this kind of like a stepwise reasoning process. So typically what it did is, it starts to sample multiple candidate solutions and then assess these intermediate steps through some kind of a reward model. And then after they update this policy model using the reward, right? And then something like a reasoning step again for the next step. So which can be represented in this way. And then for the evaluation and regulation, so we can see the difference between monitoring and evaluation. So monitoring is really about like a thinking while doing, right? It's kind of like a LM, like a solve the problem in multiple steps, then we actually need to do this stepwise monitoring. But evaluation here is actually kind of a thinking after doing. So it's more like, the model need to like reflect after the model generates some kind of a final response. So now here is, where we should get the feedback from. So lots of different ways. Of course, like a simple way is that you can just prompt LM, right, using the LM as a judge. But you could also leverage some trait critique model as what we did in our task model, right? So we actually generate some synthetic this error detection, error correction kind of a data to train the critique. And finally, perhaps like we can rely on some external tools, right, to provide the feedback signal. And finally, for the meta reflection, it's actually like, we would need to like have a certain way to get LM to gather the feedback across multiple tasks, right? So usually like this would be this bi-level approach, right? Not just refine the reasoning strategy, but then also optimize some meta level parameters as well. So some like actionable insights, I think we propose like developing the paper. I think the first one is really, we don't yet like have a benchmark data, right, to kind of measure these LMs capability for self-awareness, like introspection, reflective reasoning, and so on and so forth. And for this solvability kind of assessment, we say that we will need both capability aware kind of assessment and also this mission aware assessment, right? So we really need to have something to integrate those ways. And we need to have some way to do this adaptive reasoning strategy, like generation. So essentially, like you can imagine the input probably like need to be mapped to latent concept space or multiple kind of like potential skills. Then conditional on them to generate the answers. So you can think about this mixture of expert approach or Bayesian inverse planning. And then for this self-play for meta reward seeking, right? So basically like, this is like a move away from this kind of a more static, or we say like, this verified, external verified reliance, right? And then usually provide accurate reward, but then they are very limited. So whether there will be a way to actually generate some kind of dynamic meta rewards. And then this so-called latent space reasoning, right? So although like now we see all these like large reasoning models generate lots of like reasoning tokens. If you actually like imagine this answer seeking, it's kind of like you try to find a path from the hidden state representation of the input to the final answer, destination answer. And this intermediate reasoning kind of like tokens will somehow, give you some kind of intermediate directions, right, in order to help the model to find the final answer. Then there's no reason why this kind of like a trajectory finding cannot be performed in the continuous space, right? So I'll actually show you a quick example. So the finally is, we will need to think about like a more effective training, right? So I guess I'm probably like run out of time, but I just want to quickly show you a recent work like what we did. If we call it coding, so it's a continuous train of thought. So it's really like about this train of thoughts or this intermediate thinking can actually be performed in the latent space rather than like we rely on this kind of explicit generation of reasoning tokens. So I will just quickly show you how these things work. In fact, like what we did is we for kind of like a more feasible training, we actually consider this as a compression task. Right? We want to compress the explicit train of thoughts into the latent space, so to the implicit space. So we actually do this almost like in knowledge distillation. We have a teacher model trained on explicit COT, but we have a student model to actually like trying to kind of acquire capability of this teacher model. However, like without explicitly you generate all these tokens. So all the Z here, I think we only have a fixed number of this continuous token, right? So you can imagine the latent space. And basically like what we did is we actually anchor the representation on the column. Of course, like we also try some other things. And then we just need to ensure for the student model, the representation would somehow align with the representation of the teacher model. And then, of course, like we have the usual cross entropy loss as well. Right? So there's like more kind of details about the training process in our paper. But we can see some like interesting results here. So I think we done the kind of like reasoning on the math task. And then, so both like a GSM-AK and then also the natural language version of a GSM-AK, but then we also got the results on the common sense task. So basically like, compared to the other like implicit kind of reasoning models, our model actually performed the best. Of course, like sometimes it's still like, inferior to if you just use the COT to do the supervised fine-tuning. However, I think on the common sense QA, we actually observe our model actually outperforms you just like do the supervised fine-tuning on the on the explicit COT data. So to wrap up, I think there's still lots of things we need to do in this space. First, like we probably still don't really understand this LM self reflection well, right? So there's a still theoretical, I think, study and also empirical study to be conducted in this space, and also about reflection strategies, right? So perhaps we also need to think about long-term planning, short-term planning. I mentioned this meta reflection, and there could be a reflection augmented memory as well. And then for the data, so of course, usually you expect the training data with some explicit reasoning cues, right? But then there could also be multimodal reflection as well. I think we see there's some recent paper actually doing this training of almost like images, right? So kind of the source no longer in the text token space. It can be also in some other modality space. And model architecture as well. So because for the reflection, we probably we don't need to update all the parameters. There might be a sub-network actually would be more important for certain different types of reasoning skills. So whether we could have something to identify them and then to do more effective, efficient training. And finally, these learning algorithms, right? So I think we talk about this Bayesian meta reasoning, but then there could be also other approach to address this problem. So that's all from my talk today. Thanks.